Hi guys, good morning.
Morning,
Are you
sir.
able to hear? Yes. Okay, because I'm using a new earphone. I don't know whether it's working on this one. Okay, thank you. So yeah, so we'll start right away. Okay. So yes, people, we have been seeing ionic equilibrium, right? So like we saw, I think it's one page we just see what amount we saw, right? Okay, so we started with different theories of acids and bases, right? So Lewis theory, Lowry-Bronsted theory, and Arrhenius theory. Arrhenius theory is most common, H plus and OH minus. The Lowry-Bronsted is in terms of protons, accepting protons and giving protons. Lewis is going to be in terms of electrons, accepting a lone pair of electron, the acids, and other ways bases, right? And then we say that we're going to take a reference point for any calculations for P or say deciding strength of different species, right? So H2O is that reference point, right? And then we say we actually have to know that whenever you want to, if there's a species which gives me H plus, right? So in the medium, I should have something which can accept the H plus also. So that is the role which is played by water or any other solvent. Right. So this is how you write the reaction. HCl plus H2O gives me H3O plus Cl minus, and then yeah. So and then this is how we calculate the what is the mathematical point of view of pH, right? So here you have two molecules of H2O, one going to act as H plus acceptor, other is going to be the donor, and then you'll form all these reactions. We saw the Kw value. You have to remember it. I told you at 25 degrees Celsius, 10 to the minus 14. From here only, we'll be getting what is the pH of water. That is at 7. And we have one more formula, POH, right? And then I said you that we are not going to see about strong acids or bases here. We'll be only seeing about weak acids. And I told you the reasons. Like for calculation purposes, it is not going to be worth it. Something it's going to at some point, some quantity is going to become 0, right? Okay. So then, yeah, I told you if it's a strong acid, right? How do you calculate the pH? Whatever is the concentration of the acid, that will be the concentration of H plus also. And then you put it in the pH equation. But if it's a weak acid, no, you cannot directly put it, right? So you have to, it is obviously going to depend upon the alpha value. Hope you remember, we'll see it. Like I taught you that also, right? So, and then one more important thing, questions might come from this. Whenever the acid concentration, even if it's strong acid, if the acid concentration is lesser than 10 to the power minus 7, right? So at that time, obviously you have to take the H plus concentration coming from water also. So only then you'll be getting the pH value to be lesser than 7, or else, hope you remember the example, right? Okay. So then, yeah, this is how we go for the acid dissociation constant, in the sense that say specifying a strength in terms of numbers, right? So Ka is the one. It's going to be directly proportional to the acidic strength, right? So we got C alpha squared divided by 1 minus alpha. And I told you most of the ways, like 90% of times, we'll be just using Ka is equal to C alpha squared, right? And yeah, you can connect pH with Ka, pH with alpha, right? You just have to remember that the H plus concentration from the equilibrium table, right? I told you the equilibrium table here is just C alpha. So you just have to remember that. And if you Ka value, I mean Ka is C alpha squared, and this you remember, the pH can be easily calculated depending on whatever is given, right? And then I told you about pKa, which is whenever I told you, whenever it's P, it represents negative log. So negative log of Ka, right? And strength is directly proportional to Ka, and pKa, obviously it's going to be inversely related. Same thing for bases, exactly. But the only difference is instead of pH calculations, we'll be going for POH calculations, right? And then you have to use the formula pH plus pH is equal to 14 for calculating pH, right? Okay, and then we went on to salts. Basically, we're going for salt hydrolysis. I told you what are different types of salts, how they are formed, acidic or basic, and we even saw how do you, like, and as I told you in the questions, they will not give you whether it's an acidic or basic salts, but you have to know by looking at the salt that is whether it's acidic or basic, right? So it's just going to depend on the cations and anions that are present in the salt. You have to predict which acid the anion came from. Generally, from the acids, I'll get the anions, right? For example, Cn minus. Sulfate ion, if you get, that is going to be H2SO4. Nitrate, if you get, that is going to be HNO3. right? And say the positive charges, the cations are going to come from the bases, Na plus, NH4 plus, Mg2 plus. All these things will obviously come from MgOH, NaOH, NH4OH, or ammonia, right? Okay. So yes, and then that we saw, then we were first one for acidic, and yes. So regarding the how do you write the hydrolysis reactions, right? I told you only the weaker component will get hydrolyzed, right? So you saw from NH4Cl, NH4 plus would have come from NH4OH. So that I take and I go for the hydrolysis reaction. And how do you remember? Like you don't have to remember, like mug up anything, people. It's easy. So NH4OH was the base, right? So after removing OH minus, what I have with it is NH4 plus. That would have been the conjugate acid of the base NH4OH. So this is going to behave as an acid. That's what I'm trying to tell you, right? So this will donate a H plus to H2O, giving NH3 and H3O plus. And then I told you, you just have to remember two formulas for both acidic and basic salts. One is for KH, other is the pH calculation. Now, in case of an acidic salt, remember, if it's an acidic salt, we only worry only about the basic component, sorry, not basic, weaker component, right? So in this case, the weaker component is base. That's why you keep Kb, right? Nowhere you will be seeing Ka or pKa. You will be seeing only Kb and pKbs, right? Okay, if it's an acidic salt, because the weaker component is that base, right? Okay, so KH is this, pH is this. Hope you have to remember the formulas. It's just formula applications, right? And then the same for the basic salt, formula KH, and then the formula for pH, right? Okay, that is what we stopped. Okay, so only one more thing is left, right? So that would be, I think we'll finish it here itself. So that would be my buffer solutions. Once again. Okay, so buffer solutions. Now, first of all, we need to know what are buffer solutions and why are they, I mean, where are they used? How are they used, right? Okay, so guys, tell me, if you want to control a chemical reaction, right? What do you mean by control? If you ask me, say I want to drive the reaction more towards products or more towards reactants, or say I want only 80% efficiency, something of that sort, something you're trying to control. What do you tell me? What are the things which with which you can control the chemical reaction? What are the parameters you can use?
Concentration, temperature.
Okay, temperature, yes.
Pressure.
Pressure, yes, okay.
Volume.
Volume, to some extent, okay. Then, okay. So, fine. What about catalyst? Will that be a good choice?
Yes, sir.
Yes, catalyst. Yes. Other than that, and then one more can be a pH. Like certain, I don't know whether you know this. Certain reactions are pH specific, right? So if at all I want to give you, if I want to give you an example, KMnO4 minus is a very good example. We know potassium permanganate is a oxidizing agent, right? But its oxidizing power, in the sense that oxidizing power, in the sense how powerful its oxidizing power, I mean oxidation is going to depend on the pH, right? In the sense that I know MnO4 minus, basically, if this reaction is going to happen in acidic medium, right? Okay, if MnO4 minus is going to act as an oxidizing agent in acidic medium, obviously oxidizing agents have to get reduced, right? We'll speak more about this when we see redox reactions. Okay, so MnO4 minus will get reduced. You know how it happens. You have to calculate it through the oxidation numbers, right? So +7 here it will be, and if it is an acidic medium, if it's an acidic medium, okay, it is going to form Mn2 plus. Now the oxidation number will be +2, right? So you see there are going to be almost 5 electrons gained by manganese, right? Okay, so if it is going to be in basic medium, my MnO4 minus will become MnO2. Okay, so this happens in basic medium. So here you can see it's going to be +4. So total of 3 electrons would have been accepted. Anyways, okay. So next, if it's a neutral medium, right? MnO4 minus will become MnO4 2 minus, right? So again, it will be +6 here, 1 electron gate. Right. So you can see what I'm trying to tell you is there are not only this reaction, there are so many reactions in organic or in inorganic reactions, so many reactions where the reactions will be pH specific. Either the reaction will not happen in a, or say the reaction will happen only in a particular pH, in the range of pH. That is one kind of reactions. Or say different pHs, the reaction will give different products. So that can also be one type of other pH controlled reactions. Okay, so anyways, so at the end, what you have to understand is we have to control the pH of the reactions also in so many cases. Only then whatever the product you want, that can be extracted or that can be formed. Right. So there are something called as reaction conditions. Only in those conditions that reaction can happen efficiently. Say, as you told you all the points: temperature, pressure, catalyst, pH, concentration. Yes, obviously, right? So all these things are what are called as reaction conditions, right? So if you really take your major in chemistry, maybe if you go to labs, you will actually understand why how much important all these things are. Right? It's just a simple reaction. You see reactants products, but it's not that simple if you're going to conduct certain reactions in a lab. Okay, all these things are going to help us. Okay, so anyways, so that's where buffer solutions come. Like in a pH controlled. I'm sorry guys, just give me a minute. Just a second, guys. Sorry guys. Okay, so yeah, that's where buffer solutions come when you want to control a pH. So what happens is in certain reactions you want the the reaction will happen only at a certain pH, but say for example, we'll take some specific cases also. Say the reaction will happen only in acidic pH, like say pH lesser than 7 only, that reaction will happen, right? But assume that one of the reactant itself is a base. I hope you're trying to get what I'm saying. The pH, I mean, the reaction will happen only in a pH lesser than 7, but one of the reactant itself is a base, right? So that complicates it, right? So that time we have to use these kind of buffer solutions. Okay, so these buffer solutions are going to help us in controlling the pH, or say controlling in the sense, or in other words, I can say maintaining a pH. Maintaining pH, right? Okay, now pH, okay, maintaining pH is going to maintain one constant value of pH. pH of what, right? So pH can be controlled by controlling the pH of the buffer solutions. So whatever there basically the pH, I'll tell you how we are going to control it. The pH, what to say, the buffer solutions is pH. That is the pH you're talking about. Whatever is the buffer solutions pH, that will be the reactions is pH also, right? So you will be able to tweak it, right? Okay, now how we are going to do it. Now, depending on what causes you the problem, in the sense that whether it's an acid which is in the reaction which is causing me a problem, that means you want to neutralize the acid, or say not neutralize, making sure that the acid doesn't affect the pH, like that way, right? Okay, and say I have a base, and depending on that, basically I'm telling you, depending on what is there, what is causing the problem, buffer solutions can be of two types. So we know that it's basic buffer and acidic buffer. Okay, right. So how do we first, this is the types, how do we create this, how do we form this, right? Fine. So first, a basic buffer, right? So whenever base is causing you a problem, right, you want to make sure that the base is not increasing the pH. Generally bases increase the pH, right? So due to a base, you don't want the pH to increase. That time you go for a basic buffer, right? So you can even write it as for bases, right? Okay. Now, how do you produce it? It's very simple. You take a weak base plus you take salt of this weak base, whatever this weak base you took here, that salt of the weak base that you take, and you mix it. And the concentration, like how much you have to mix, that is going to depend on what pH you want. Okay, that I'll tell you now. That I'm going to give you a direct relationship. There are derivations. There are inside theory, like not theories. There are inside derivations, mathematical equations there. But I'm going to give you the end result, how the pH and concentrations are connected. Okay, so basic buffer. Okay, fine. So how do you calculate the pH depending on? Okay, before that, let us give you some examples, right? What can be examples? So we have to add a weak base and a salt of the weak base. Say for example, I can take any weak base. For example, NH4OH, right? Plus, I have to take the salt of this weak base. What can be the salt of this? Can you tell me? Any examples? Okay, so what I'm trying to ask you is, if this is the base, right? If this reacts with an acid, I'm going to produce a salt. You can tell me any salt with basically NH4 plus. That's what I'm telling.
Ammonium chloride.
Yeah, NH4Cl would be a good choice. Right, so hope you understand, right? You have to take a base, right? And obviously the cation, that should form a salt when it reacts with an acid. Like that salt you will take. Any ammonium nitrate, ammonium carbonate, yeah, exist, right? But ammonium chloride will be a solid standard example, right? Okay, so that's how you produce it, right? So now the pH calculation I'll give you for basic buffer, right? If you want another example, say I can even take aluminum hydroxide with aluminum nitrate. Right? I'm sorry, this 3 should come out. Yeah. Right. So that can also be an example. Again, a weak base, aluminum hydroxide, salt of the weak base. So again, you see the cations are common. That's what you need to understand. Okay, fine. So pH is pKb plus log of salt concentration divided by the base concentration. Oh wait, it's not pH, guys. Since we're talking about basic buffer, I'm really sorry. This is going to be POH. Okay, since you're talking about basic buffer. Sorry. Okay, so you can see, right? This is the formula. Only one formula to remember. That's it for the basic, or one formula for basic buffer, one formula for acidic buffer. Right? So POH is equal to PKB of the weak base. You're using NH4OH in this case, right? And you can see log of this whole thing, the salt concentration and the base concentration, whatever the concentrations you take. Right? Fine. So that's very simple. Right. Next we go for acidic buffer. Now, how do you produce it? It's going to be very, again, for acids, you use this. Whenever acids are causing you problems, at that time you go for acidic buffer, right? Yeah. So then how do you produce it? So you have to take a weak acid plus salt of the weak acid. That's it, right? So again, there can be so many examples. Any examples you want to give me for acidic buffer?
And sodium acetate.
Yes, good. That's a good example. So weak acid CH3COOH plus, again, you see now in this case for acids, anions are going to be common. You just remove the H plus, and then you put another cation, metal ion. So very simple. So CH3COON. That's an example. This mixture in some ratio is going to be an example for acidic buffer, right? So next, I'll directly give you the pH. Now, remember last time it was pOH. So in this case, it's going to be pKa plus log of salt concentration. That's fine. Divided by the acid concentration. Simple again, one more formula. Okay, right. Now that's it. The chapter is over. Now the one question, if you ask me, sir, how this is going to control the pH, right? So that's pretty simple. I'll tell you how, right? Like, let me take an example for acidic buffer, right? So I said there is an acid, okay? There is an acid which is going to give me H plus, right? So there is an acid in the reaction which is causing me problems, right? Now that is giving me H plus. Okay. Now what you see here is I have CH3COO minus. For example, if I'm going to take this, if I have what is this? CH3COO minus is going to be there. Now you see CH3COOH is a strong acid, right? So I know the conjugate base of a strong acid is a I'm really sorry. This is a weak acid, right? So the conjugate base of a weak acid is a strong base, right? It's always ulta, right? Strong base, weak conjugate acid. Say, hope you understand, right? So in this case, it's a weak acid. So its conjugate base will be strong. So in the sense that it will be able to accept H plus in a very efficient way. That's what I'm telling, right? So this reaction is going to happen. You form CH3COOH. This reaction is going to be favored and not the opposite way. Or whatever is this, like this H plus is actually going to make sure that this reaction moves only in this direction also. So making sure that this H plus also doesn't come out, as well as the H plus which is coming from the acid is also getting neutralized. That's what is going to happen. But anyways, even if you, this is not much of a deal. You don't have to really understand how it works. There are so many other theories. Which is one of the way of explaining. Anyways, so you just have to remember the pH formulas. How do you form the acidic buffer, basic buffer? And that's it. Examples. Yeah. That's enough, right? And the next problem you will face is when I go for the numericals, right? So you will find it difficult to understand whether the problem is coming from buffer solutions or say the problem is coming from salt hydrolysis. So because in both these things, we'll be calculating pH, there are salts, there are acids, there are pKas, pKbs, everything is there. Right. So how do you, and the data is also will be like that only. You will not be able to understand, right, which formula to use. But I'll tell you a trick, right? So look at here, right? So in this buffer solutions problems, right, you will see two concentration values given. Okay, two concentration values will be given. One for the salt and one for the acid or the base, depending on what type of buffer it is. Right. And in the questions, they'll not tell you that it's buffer or salt. They'll not tell you. Right. So there'll be two concentration values given. One concentration value is for the salt, and the next concentration value will be for the acid or the base, depending on what type of buffer it is. Right. But if you go to the salt hydrolysis, let me show you. You see, say this is what? This is my basic buffer. Okay, so you see, there is only one concentration required, and that's the salt concentration in case of salt hydrolysis problems, right? And this thing is the base or acids concentration is not required. Not required in the sense, if they give you, that means it is buffer solutions. If they don't give you, that means it's salt hydrolysis. Is it okay? Right? So that is how you identify. So in case of buffer solutions, two concentration values, and in case of salt hydrolysis, there'll be only one concentration value given in the question. Based on that only, you will judge whether this question is from this or that. Okay, so that's it. We'll do some good number of problems and we'll wind up this chapter. Any questions, people? That's it. We'll just go for the problems. Yes, okay. I hope there are no questions. Fine. So I'll just WhatsApp you same way. We'll do that. The questions. So yeah, question is there. Question number 7, which is marked. I hope the picture is clear. The lighting is not that proper. Okay, so the question is 200 ml of aqueous solution of HCl of pH is equal to 2 is mixed with 300 ml of an aqueous solution of NaOH, which has pH 12. So they're asking, what is the pH of the resultant solution? Right. So guys, in this case, you have a strong acid and a strong base, right? That is HCl and NaOH. So tell me, if I have a strong acid and a strong base and neutralization will happen, right? So what will be the pH of that particular solution?
7.
7.
Okay, 7. Right, that's what we expect. Now, like this case will happen only if the acid concentration, or say the number of moles of acid and the number of moles of base is going to be same, right? But what if something is in excess? At that time, how will you how will you decide the pH will be okay in this range or in this range? Did you understand the question? I'm asking. Now you said the pH will be 7, and that so I told you that this will happen only if the number of moles of acid and number of moles of base are same, right? So now asking, if that is not the case, if the pH is not neutral, right, or say there is among the acid and the base there is one thing which is in excess, but they're not equal. They're not equal number of moles. One thing is in excess. So then tell me, depending on what you will decide what range the pH would be in.
So if the concentration of acid is higher, then the pH is less than 7.
Okay, that's how you do it. Depending on if the excess reagent is an acid, then it's going to be lesser than 7. If the excess reagent is a base, then the pH is going to be greater than 7. Right. Now tell me, guys, first you do the I hope you remember something about stoichiometry, right? So can you just write the reaction and tell me whether this reaction has any excess reagent or not, or say this reaction has any limiting reagent or not? You try. Anyways, I'll help you. Okay, and there's one formula which I forgot. I mean, the formula, you already know the formula, just the other variant of the formula. I know pH is negative log of H plus, right? But if I ask you what is the H plus concentration, if they give you the pH value, the direct formula is H plus concentration is 10 to the power minus 10 to the power of minus pH, right? This you use. And say the other formulas which will be helpful is molarity is equal to number of moles by volume, because you're going to do the stoichiometry in terms of number of moles. Remember that. Okay, did you find anything is in excess?
So NaOH is in excess.
Okay, so as you say, NaOH is in excess. Fine, so we'll find it out. So I have HCl. plus NaOH gives, actually, I don't have to go beyond the this thing. It gives products, that's it. Because anyways, that's not going to be useful for me. Right? Okay. So HCl, they have given me, what is the data? They have given 200 ml of PH2, right? So can I say it will be 200 ml of 10 to the power minus 2 m HCl? They're giving me pH2. So I'm just taking H plus concentration to be 10 to the power minus pH. And since it's a strong acid, I'm taking directly the concentration of H plus to be the concentration of the acid. That's it. Right? So this is the concentration of my HCl, 10 to the power minus pH, that is 10 to the power minus 2. P is given as 2. Right? Now I can easily calculate the number of moles. Right? So molarity is number of moles by volume. So you can see number of moles would be molarity into volume. Right? So this would be 200 into 10 to the power minus 2. Sorry. So that would be, it's already in ml, right? So you can do it in terms of millimoles, right? If it was in liters, you can directly get moles, but since you have ml, you're going to get in terms of millimoles, right? So it will be, can I say 2 millimoles, 200 into 10 to the power minus 2, right? 2 millimoles. Okay. Next, I have 300 ml of, okay, now you cannot directly, I think, do this. So they're giving me pH to be 12, right? So if at all you want to find OH minus concentration, you have to find POH, right? So that would be 14 minus this, that is 2, right? So from this, I can easily find the OH minus concentration. Exactly similar. It is going to be 10 to the power minus of POH. And in this case, POH is 2, right? That will be 10 to the power minus 2 M. Okay, it's 2. Why is it not coming? Okay, 10 to the power minus 2. So that's what you need to understand. So it will be 10 to the power minus 2. I hope you understood what I did here. They have given me pH. I calculated POH. From this, I calculated OH minus concentration. Same formula as H plus concentration. 10 to the power minus POH in this time. Fine. So done. So in this case, it will be, I think you can easily find how many millimoles it will be. This into this. That will be 3 millimoles. So as you said, yes, you can see here it's 2 millimoles. If the stoichiometry says 1:1, right? So 2 millimoles require 2 millimoles, but I have here extra 1 millimole, that is to be 3 millimoles. So this NaOH is my excess reagent. I just write it as ER, right? Excess reagent, right? So obviously what you find is this, whatever 2 millimoles of H plus I had would have been neutralized by 2 millimoles of OH minus. Right. So there will be excess amount of OH minus ions. Can I calculate what is this excess OH minus number of moles? Easy. How much it will be? Excess means what will be remaining even after the reaction. How much will be remaining?
1 millimole.
Correct. Right. So 2 millimoles would have reacted. 1 millimole is left. Right. Now I have to calculate the pH of the solution. Now the pH only is going to be because of this, because other things got neutralized, right? Okay, so now I know the number of moles. I have to calculate the concentrations first, right? So that will be 1 into 10 to the power minus 3. 1 second. Then 10 to the power minus 3 is coming from number of moles by volume. 1 into 9. Okay, volume is total. You see how much they're adding? 200 ml of acid, right? And 300 ml of the base. So total is 500 ml. That volume only you should take, but because everything is now together, right? So you take that volume, total volume, that is acid plus base, whatever the total solution I have, that is 200 plus 300 will become 500. Okay, fine. Now, since it is an ml, right, you have to put 1000 also. Right, so 10 power minus 3, 10,000 gets cancelled. So it is going to be 1 by 500. 1 by 500 is 2. It will be 0.9 0, 0, 0.0. Yes, 0, 0, 2. Okay, done. So that's the OH minus concentration. Now I can easily calculate the POH. From POH, I can calculate the pH. That's it. POH would be negative log of 2 into 10 to the power minus 3. Right? So now you have to know the log values as I told you. Right? So you can easily do the log value. It will be actually 3 plus or minus 3 minus 0.3010. Hope you know how I did this. This is log of AB, right? Log of AB I can write as log A plus log B, right? And you can see 10 to the power minus 3 is here. The minus 3 can go in here. So that'll become plus all these things. Hope you know. Like, do you want me to explain the log calculations, guys?
No, sir.
Okay. Hope you understand the log calculation, right? So now whatever the value, it will be around 2.7. Right, that is my POH. So pH would be again 14 minus this value. So it will be 12, 11.3. That is the answer to this question. So I can see the answer to be D. Okay, right? I'll just give you a very quick thing of what I did. Very simple. So I just said I use formulas of what is the H plus concentration and OH minus concentration in terms of 10 to the power minus H plus and 10 to the power minus POH, right? And that's it. And then I calculated the number of moles, 2 millimoles and 3 millimoles. And I found out the excess reagent is NaOH. Then I know the excess number of moles remaining in the solution is 1 millimole. And then I calculated what is the concentration of that, making sure that the total volume I took 200 plus 300, right? And then I found the concentration, then I found the POH, then I found the pH. That's it. Simple. Okay, so when I did it, it took little time because of explaining you. But if you really practice, it will not take more than a minute for you to, if it's calculate again, given that the calculations are pretty simple. Okay, fine. So I hope everybody understood. The next question. So we'll do a question which came in JEE Mains 2014. That's what the book says. Okay, question number 11, which is marked. It's based on the JEE Mains 2014. What is the time? Okay, so the question says, how many liters of water must be added to 1 liter of an aqueous solution of HCl with a pH of 1 to create an aqueous solution of pH of 2? So what they're telling, already I have 1 liter of some solution, HCl solution, that is having a pH of 1. They're asking, how much more water should I add so that the acid becomes diluted and its pH becomes 2? Think about it. Time is 10:46. I'll give you time till 10:50. At least if you come up with an approach, that would be nice in this 4 minutes.
Sir, is the answer 9 liter?
I'll check that for you. Yeah, answer is 9 liters. Yes. Good. Very nice. Okay. So almost time is going to get over. If anybody also gets me an answer, please tell me. Okay, fine. I'll try to solve it. So they have given me 1 liter. 1 liter, what is it? HCl? Okay, 1 liter HCl with pH of 2. pH of 2? Sorry, pH of 1. Sorry. Right? So I can easily see the H plus concentration to be 10 to the power minus 1 m. Or I can say this is the concentration of the acid also. Doesn't matter. Right. Fine. So now what they're telling is I want the pH to be equal to 2. So that means I want the concentration to be 10 to the power minus 2m for the HCl. Right? Okay. So now you can easily see what is the number of moles here, right? From this for this one, right? Number of moles of H plus HCl, whatever they can even keep HCl if you just don't want to confuse yourself. Right? So number of moles of HCl will be again a molarity into volume. That will be 10 to the power minus 1 into 1 liter, which will be 0.1 moles. Right? Now I want, see, we'll okay. Fine. Now you remember that you're just adding water here. Right? You're just adding water here. That means whatever is the number of moles of HCl you initially had, right, before when the pH is equal to 1, right, that number of moles is not going to change. Yeah, right? That number of moles is not going to change. So you're just going to add more and more amount of water, right? So that means for this particular solution where I have added water, the number of moles of HCl will again be 0.1, and that would be equal to 10 to the power minus 2 into the volume, whatever the extra. Now, this is the total volume of water present, not the volume you added, right? This is the total volume of water present, right? Now, I think that you can easily do it. That will be let's say 10 to the power minus 1 and 10 to the power minus 2 will become 10 to the power 1. Am I right? Yeah, 10 to the power 1. That means there is 10 liters. Right. Now this is the I think I'll write it here, guys. Right. I have now 10 liters of H2O. That's what I calculated here. Right. Okay. That means 9 liters. 1 liter was already there. Where was it? Oh, sorry. Here. 1 liter was already there. Right. Now that means I would have added extra 9 liters. That's what they're asking. How many more liters of H2O you should add to convert the pH from pH equal to 12 to pH is equal to 2 by diluting, by adding more water. Right? So this is a pretty simple problem. I hope everybody understood. I calculated what is the number of moles of HCl present in the very first solution and that number of moles is not going to change because you're just going to add more amount of water rather than removing number of moles, removing HCl. That you're not doing. If you're doing that, yes, the number of moles would have changed, but you're just adding more and more water, right? So accordingly, the number of moles here, and even if you are more water, the number of moles is going to be same. That means molarity and the volume calculations can give me the number of moles, and I got the volume. To be sorry, 10 liters, and then extra added is 9 liters. That's the answer. Pretty easy question, right? Okay. If any doubts, you can ask me. I'm going to the next question. I'll send you in the group. Okay, so question marked 5. pH of 0.08 mole per decimeter cube. Remember, 1 decimeter cube is 1 liter. Okay, right? That's the conversion. 1 decimeter cube is 1 liter. 1 centimeter cube is 1 ml. Okay, please remember this. I can write it for you if you want. 1 decimeter cube is 1 liter. 1 centimeter cube is 1 ml. Right? So these two you can remember. So pH of 0.08 mole per decimeter cube HOCl is this much. What is its ionization constant? What do you mean by ionization constant, guys? What they're asking? What are they asking? Which term they're asking? What is what is that? Ionization constant. Ionization constant? Any guesses at least?
K,
From
sir.
it is definitely
K.
right. K. Correct. Dissociation constant, ionization constant. All these are the different names for K. Okay. So they're asking about K, but unless they ask you what is the percentage dissociated, what is the extent of dissociation, degree of dissociation, all these things they ask you, then they're asking you alpha. Okay. Right. Fine. Go for it. Use all the formulas. I told you you can tweak it. If it is no two things. Okay, so time is 10:57. I'll be back by 11 o'clock. You do that problem. Okay, 1 second. Yes. Any answers? Yes. No answers. Okay.
Sir, is it B?
B, that is 2.5. Okay. Fine.
Yes, sir. B, sir.
Okay, we'll check. Fine. So we have given pH to be pH to be 2.85. So my H plus, or say the acid concentration, would be 10. Oh, okay, fine. But okay, fine, cool. Fine, 2.85. So, but they have given some anti-log value of 0.15. So if I can do that, 10 to the power minus 0.15, if I take out from that, what is remaining? 2.7. Oh, that will not be working, right? Or why did they give that value? 0.15. Or what is the other? Okay, this will work. No, 3 minus 3 plus 0.15. Right, that will be 2.85 minus 2.85. Right, that will be fine. So this would be basically 10 to the power minus 3. Okay, into 10 to the power.
Sir, they've given the anti-log for 0.15.
Yes, that's what I'm doing. Wait, what? I'm coming for that. Okay, right. So if I take the anti-log, right? So basically, or I got actually I have done it in previous this thing itself. Correct. So negative log H plus is 2.85. Anyways, it's the same. So anti-log means basically 10 to the power minus 0.5 is only this thing, anti-log. Hope you understand. Oh, like see, log of something A is some B, right? So what will be, how will I write it? A is 10 to the power B. This is how I write it. Okay, this is how the log works, right? So this 10 to the power B is what is called as anti-log of A. Hope you understand. Okay, this 10 to the power B, what you write here, you reverse the operations, right? So, or I would say ln and e power x are again inverse functions, right? That again is, I'll call the anti-log only, but that will be in natural logarithms. Okay, e power x or whatever it is. Okay, so this 10 to the power minus 0.15 is what is the anti-log, and that value is 1.41. No? Okay, 1.4. Okay, 1.41. Right, so done. So I think that I got the H plus concentration. I mean, H plus concentration, I got the pH value from that. Whatever is the actual H plus concentration dissociating, that I got, right? But if you see, what is the actual total concentration of the acid? The total concentration of the acid is 0.08 m, right? And from this, I'm actually getting how much? I'm actually getting only, what is the value? 1.41 into 10 to the power minus 3. Yeah, 10 to the power minus 3. Okay, right. Anyways, so you can understand that means it's not a strong acid. That's what you need to understand. Okay, fine. So for my Ka, I just require the concentration of the acid that I have with me and the alpha value if I have done C alpha square. That's it, right? Okay, so how can I find it? So it's pretty easy, right? So if I write the acid HOCl, gives me H plus, and whatever it will be OCl minus, right? So I have 0.08 here, and I have this thing, say, okay, 0 at equal, okay, fine, I'll just directly write it. It's going to be 1.41, right? So can I say, why am I so much doing? I can use the formula. pH is negative log of C alpha. Hope you remember the formula, guys, right? So pH is negative log of C alpha. It's pretty, now it's, I think it's pretty easy. So it'll be pH, I know it's 2.85. So log of concentration is 0.08. Right, alpha we don't know, right, is 2.85, right? So I can write 0.08 into alpha is 10 to the power minus 2.85, and this I found out to be 1.41 into 10 to the power minus 3, right? So alpha value would be this divided by 0.08. Done. That's it. I got the alpha value. Now you substitute it here. That is in the Ka equation here. Oops. Right, Ka is equal to C alpha squared. Done. So C is 0.08 and alpha value I found out 1.41 divided by 0.08. So let me check the answer if what you said was correct. What is the question number 5? Yeah, 2.5 into 10 to the power minus 5. That's the answer. B is the answer to this question. Okay, right? Pretty easy. I just quickly give you a recap of what I did. Right? So they're giving me pH. I think it's pretty easy. I can just use the formula. Two formulas. Ka is equal to C alpha squared and pH is equal to negative log of C alpha. Done. So pH is 2.85, C is 0.08. Alpha, if I find Ka, I can substitute and find out. That's it. Right? So alpha, what I said? Yeah. Right, and this pH is 2.85, and if I take the anti-log, it will become 10 to the power minus 2.85, and that value I could find, I found out to be 1.4 and 10 to the power minus 3. So alpha I found out, C alpha squared I can do, find the Ka. Done. Answer is 2.5 into 10 to the power minus 5. B is the answer to this question. Okay, I hope everybody understood. Okay, guys, actually, what is the time? 11:10. I actually forgot one topic to be taught itself, other than buffer solution. Buffer solution is not the last topic. I'm really sorry. There is solubility products. Okay, this I totally forgot. Important. This is actually very important. Okay, actually in 20 minutes, I'll be able to complete it. Okay, fine. So solubility, okay, fine. So we, like in this, what we're going to do is we're going to take sparingly soluble salts. In the sense that they will not be, and sparingly soluble, they'll be very less soluble salts. Okay, now why am I taking less soluble salts is because they will easily give me saturated solutions. Hope you know what is a saturated solution. Okay, saturated solution means I mean, not any more amount of solute cannot be added. Right? If you add it, I am going to have precipitation happening. Please remember that. To a saturated solution, right? If you're going to add more amount of solute, right? So it is going to form a precipitate. Okay, so this sparingly soluble salts already they are less soluble. Obviously, that means they will easily form saturated solutions. Okay, right? So like this precipitation actually is used in so many in case of so many applications. Say for example, in colloidal solutions, in stability, like making sure that the colloidal solutions are a little stable, in gels, so many things and so many stuffs, right? Fine. So we'll just try to again give a mathematical aspect to the solubility. Okay, fine. Now first you have to understand what do you mean by solubility, Okay, I have to give you the definition first. What do you mean by solubility? Okay, again, it's a mathematical definition I'm going to give you, right? So it's pretty simple. It is the amount of solute, right, required to make a saturated solution. I would say in a given amount of solvent. Say I have 1 liter of solvent, right? So in that solvent, how much amount of solute I should add to make the solution saturated, right? That is what is called as solubility. Okay, so when I say S, right, this S talks about in the solution, what is the concentration, or say what, and that amount can be anything actually, isn't it? Right, this amount can be number of moles, this amount can be mole fractions, this amount can be mass, concentrations, it can be anything, right? So this S, generally it will be molarities because we are using molarities, right? It is the molarity of the salt, or say it is the molarity of the solution which is actually saturated, or say if it is given in terms of number of moles, it is the number of moles of the solute present in the saturated solution, where we talk only about saturated solutions. Okay, right, fine. So we'll give a little more mathematical aspect to this. Now, if at all I want to understand, right, I want to understand at what point the precipitation happens, right? Or how can I make sure that, okay, this is quantitatively how much salt I should add to prepare a saturated solution, and how to check whether the solution is already saturated or not, right? All these things can be done with the help of little amount of mathematics. Okay, so two things are going to help us, right? One is what is called as KSP, the other one is what is called as KIP. Okay, so KSP is this solubility product. Okay, KIP is what is called as ionic product. Okay, KIP is what is called as the ionic product. Okay, so by comparing these two values, right, I'll be able to predict certain things. One thing is whether the solution has reached saturation or not. That one thing I'll be able to find out, right? And again, our other thing would be if I add how much amount of solute is a little more add, the precipitation will happen, right? So all these things can be found out, right? So eventually what you're trying to find out is whether the solution is saturated or not, right? If I have to add more amount of solute, all these things can be calculated. Okay, fine. So first we'll talk about this KSP, right? So let me take some examples and let you know, right? So let me take some sparingly soluble salt such as AgCl, which is not that soluble in water, right? So it is gonna, I know it's gonna give me Ag plus Cl minus. Okay, fine. So if it's solubility product, remember that I'm always talking about saturated solutions, right? Say if the solubility of AgCl was S, that means this is the amount of AgCl present, right? Obviously, according to stoichiometry, you can see it's going to be S and S here, right? So solubility product is the product of solubilities of the a cation or anion. Okay, solubility product of solubilities of the cation or anion present in the salt. That's it. So if I write the KSP here, that would be S square. Okay, so how they'll ask questions is they will give you KSPs of different salts, right? And they'll ask you which salt is more soluble in water, something like that. Okay, so from the KSP value, like you can see, if at all I ask you, they give the KSP value and ask you the solubility, it is going to be root of KSP. Okay, in case of this kind of salts, right? AB kind of salts. Okay, next, if say I have a salt like MgCl2, it's not sparingly soluble, but I'm just giving you an example. Now it's gonna give me Mg2 plus 2Cl minus. Okay, so if this is S, right? Now 1 mole of this gives 1 mole of this, so this will be S, but 1 mole of this gives 2 moles of this will be 2S. Please remember that. Okay, now if I write the KSP, now remember this KSP is also like a equilibrium constant. That means whatever you followed for equilibrium constant that powers whatever you put, you have to do that. This is the concentration of, okay, this is equal. Okay, so this is the concentration of Mg2 plus S, right? And this is the concentration of Cl minus, but since you have a stoichiometric coefficient of 2, you put a 2 in the power, right? So now this will become 4s cube, right? Say something like if I have AlCl3, can you tell me what will be the KSP in terms of S? Can you quickly tell me? Okay, I'll not do it. I'll just give you a minute. Quickly tell me what it will be.
Sir, 27 S power 4.
Yeah, I think it's correct. So if this is S, this will be S, this will be 3S. So if I write the KSP, it will be S for Al3 plus into 3S for Cl minus. But since I have a stoichiometric coefficient of 3, power 3 should come. So this will become 27 S to the power 4. Yes, correct. Okay, fine. So it's pretty simple. Any salt given now, you'll be able to do it, right? You have to make sure that the stoichiometry you do properly, and also making sure that where you put the powers of the stoichiometric coefficient when you write the KSP. That's it, right? Okay. Now this is about the solubility product. Okay. Now this doesn't end, like only solubility product is not going to be really helpful. You have, as I told you, these two values to be compared. That's the application part. Okay, fine. Anyways, so now if I talk about the ionic product, okay, IP. Okay, so now it's not, now this solution might or might not be saturated. Now last time there was a constraint that the solubility, if you're going to take, we speak only about saturated solutions, right? Now this is the actual, say in this can be any real-time calculation, in the sense that the solution, we don't know the solution is saturated or not, but whatever the concentration of this cation or anion you have, that product is what is this. Say for example, if I tell you I have a 10 to the power minus 3 m say NaCl solution, right? Now the ionic product is pretty simple. The ionic product will be, now you know, from 1 mole of this gives me 1 mole of Na plus and 1 mole of Cl minus, right? So obviously it will give me 10 to the power minus 3 m of Na plus and 10 to the power minus 3 m of Cl minus. Right? So can I say the ionic product will be 10, or I would put it like this. It will basically be the concentration of Na plus, whatever the concentration you get, it need not be at saturated state. Now that would be 10 to the power minus 3 into 10 to the power minus 3 will become 10 to the power minus 6. Okay, 10 to the power minus 6. Right, this is what is ionic product. Very simple. You don't have to do much whatever you did like an ionic product. Whatever the concentration of salt you have, you just do the stoichiometry and put the ionic product. Okay, pretty simple, right? Again, if you have this thing MgCl2 and all, you have to put the square. Obviously, that and all you have to do. For example, if I have say AlCl3, right? Say I say that I have 1m AlCl3, right? So I will please remember the concentration of Al3 plus from this will be 1m, and concentration of Cl minus from this would be 3m, right? Okay, and you can see this will dissociate to form Al3 plus 3Cl minus. That is obvious, right? Now if I write the ionic product, it will be concentration of Al3 plus into concentration of Cl minus into the power 3 should come. Obviously, that is similar because both are something related to equilibrium. Okay, right? So this is pretty simple. That would be 1 into 3 power 3, which will become 9. Oh, no, 3 power 3 will become 27. 27 m. I would not write the actual units. It's 27. Ionic product is 27. That's what you need to understand. Okay, so like this, you calculate the ionic product, but that solubility is purely only for saturated solutions. Okay, now if you compare these two values, ionic product and the solubility product, I told you that you'll be able to predict whether the solution has reached saturation or not. Right now, it's pretty simple. Right now, I take some cases. Case 1. Right, if you find that the ionic product is lesser than the solubility product, right? Now, what do you mean by this? That means the solubility product is higher. That means the in somewhere in between, right? The concentrations or salts, the cation or anion are not sufficient to be equal to this. That means what? That means the solution is not saturated yet. This is an unsaturated solution. Because I told you this is real-time calculation, right? Whatever the actual concentration of the salt is, that is there. This is for saturation, right? So if I find in between that the ionic product is not like it's lesser than KSP, that means it has not reached saturation. The amount of cation and anion are not enough to cause saturation, right? This is an unsaturated solution. So if I find that the KIP and the KSP values are same, then that's saturation point. This is a saturated solution for no doubt, right? Okay, now that is actually case 2. I should have mentioned it. Okay, this is case 2. Case 3, right, would be the ionic product is greater than the solubility product, right? Now that means what? You have added more than what is required. This is real time, right? You have added more than what is required for saturation, right? That means here, okay, PP shun is precipitation. Okay, bear with it, right? So here that means you are going to cause precipitation. Okay, so 3 cases. KIP lesser than KSP, it has not reached yet saturation. If it's equal, saturated. If you add more than that, then precipitation will happen. Okay, so this is what I want to tell you. This is about your solubility product and ionic product. Okay, right? So what is the time? Okay, it's 11:24, 11:25. Okay, guys, you can just be free for 5 minutes, right? So I'll stop here, right? So I hope, did you get the schedule? From tomorrow you have class?
Not yet, sir.
You didn't get it?
Not yet, sir.
Oh, okay. So I don't know. Fine. Anyways, so if you get it, then there is class tomorrow. If you don't get it, there is no class. Okay. Fine, guys. Thank you so much. We'll meet again.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you.